In terms of protein levels of structure, the tertiary structure actually involves folding of the R groups. So if you remember primary amino acid sequence, the primary structure is just letters, nothing really three-dimensional about it. And the secondary structure is hydrogen bonding across the peptide bond. So we'll have either an alpha helix, a beta sheet, or a random coil. And now we're focusing on tertiary structure. When you start including the interactions of these side chains of the amino acids, that's when you start to have more of what's called the polypeptide fold, and then it adopts a three-dimensional structure. So the most classical example of tertiary structure is disulfide bonds in cysteine. So when two cysteine molecules come together, through their SH side chains, you'll get a disulfide bond. So that's a classic example. Hydrophobic interactions, example probably would be the side chains of phenylalanine with a tyrosine, maybe a side chain of valine with an isoleucine, a side chain with a valine with a phenylalanine, anything that involves hydrophobic stacking. In fact, phenylalanine stacking with that big aromatic ring is very common, but it also has some dangerous effects. Could be a potent aggregating force. So the cell must balance between aggregation, which is bad, and stabilizing a proper thermodynamic structure to get the native state, which is good. Hydrogen bonding can occur amongst the R groups. So the classic example of this would be the side chain of a lysine with the side chain of an aspartic acid at physiologic pH. At physiologic pH, that becomes aspartate. And you can get hydrogen bonding there. You can get hydrogen bonding between a serine and an arginine, just off the top of my head. So there's so many potential possibilities of hydrogen bonding that occurs. Also ionic interactions. That's with acid-base or plus-minus interactions, such as lysine is positively charged at physiologic pH, and the side chain of aspartic acid is negatively charged, aspartate, so you have a plus-minus electrostatic interaction. Histidine is a side chain that's positive or basic at physiological pH. Remember that imidazole group, and that could have an ionic interaction with something that has a side chain that's negative at physiological pH, maybe aspartate or glutamate. Lysine, histidine, and arginine are the basic amino acids. Aspartate and glutamate are your acidic amino acids. So you can have an ionic interaction there. So combining all of these primary forces, you can start developing a tertiary fold. So now, if you look at this diagram, you do have elements of secondary structure with your beta sheet, alpha helix, and random coil, but now you're starting to adapt a different fold. It's starting to assume a more globular nature. Tertiary structure generally gives a more globular nature. So let's recap what's happening here. We talked about the peptide bond, and the peptide bond, hydrogen bonding amongst the peptide bond, this planar backbone, is the source of secondary structure. And here's some of the bond lengths and angles, pretty much conserved. We also set aside dihedral angles, phi and psi, so that's maintained by the peptide bond. And we also have steric clashes. So you want to minimize steric clashes in your secondary structure and your tertiary structure. So these are the two main forces, secondary and tertiary structure, where you have to maximize all these forces and maximize all these hydrogen bonds, but you also have to prevent molecules hitting one another. And then in that situation, you do receive the optimal three-dimensional fold of the protein. The Ramachandran plot is a very important and pivotal part of determining secondary structure. Let's take some time to explain this. First of all, the Ramachandran plot has to do with dihedral angles. So here you'll have phi on your x-axis, and you'll have psi on the y-axis. Another important thing to realize is that this is a contour plot, so you're actually looking down on the graph. Imagine you're a helicopter, and you're the pilot of the helicopter, and you're looking down. So when you look down on something, that is a contour plot as opposed to looking at it face to face, which is how you would normally see a graph with points. You don't have points here because you're looking at contours. You're looking at regions that are acceptable, and you're looking at hotspots. So here you have hotspots of beta, here you have a hotspot of coil, and here you have a hotspot of alpha helical, and here you have a hotspot of left-handed alpha helices. It's just where the alpha helix is in a left-handed coil, whereas our typical alpha helices, if you remember the right-hand rule from physics, it actually coils with a right hand with your thumb going along the vertical axis. So most helices are right-handed. What you see here is the accessible and allowed dihedral angles for phi in the x-axis and psi on the y-axis. So for example, if you're given a dihedral angle of -90 and maybe -80, then you have a dihedral angle that is permissible for a right-handed alpha helix. So if you get a stretch of dihedral angles, that stretch of dihedral angles may be permissible for an alpha helix, or it may be permissible for a parallel or anti-parallel beta sheet. Notice here that, like I said before, these are hotspots, so you have a lot of leeway and a lot of breathing room, because remember, you have to take into account side chains, which allow for a number of different conformations. So this was very instrumental at that time, the Ramachandran plot, because it actually tells you important parts of accessibility. You would expect, for example, the amino acid glycine to experience all types of dihedral angles. You would expect the amino acid proline to maybe not experience the full conformational range because of its cyclic amino acid structure. So there's a homework assignment if you look at homework 3. If you look at homework 3, you're actually given a stretch of dihedral angles. Here's your phi angle, and here's your psi angle, and you're given the primary amino acid sequence number. So if you look at the first one, -61 and -44, -61 would probably be around here, -44, -61 would probably be somewhere around here, -44 would be 0, -45, probably around here. So that is a dihedral angle that's more permissible for an alpha helix. So let's check the other dihedral. -72 and -29, and -66 and -65. So -72 would be around here, -29 would be probably around there. Let's take a look at our third dihedral angle. It was -66 and -65. -66, probably around here. -65, probably around here. So let's take a look at our fourth and fifth dihedral angle. -67, this is probably -67, -43 is more in the blue region. -81, -51. -81 is close to -90, and -51 would be around here. So you see here that that stretch of amino acids, those 5 or 6 amino acids, would be alpha helical. And then you would continue to test the other sets of dihedral angles to see if it lands in one of these spots. Here you have primo real estate for a parallel or anti-parallel strand, and you have some real estate for a coil. So you have really good real estate around here for an alpha helix. Again, this is based upon side chains, which determine your dihedral angles, where they settle upon. And then you have so-so real estate here. Here you probably have suboptimal, but just enough for the dihedral angles to get into a right-handed alpha helical fold. So that's the Ramachandran plot. It was made roughly in the 1930s by V. Ramachandran, and it led to him to win the Nobel Prize in chemistry, because it really allowed us to go from the primary amino acid sequence to the next step. And And that next step would be to the secondary structure. Ultimately, that's what we're interested in, going from primary to the secondary structure via using very little computing power and just using a propensity or just using some sort of scale. So Ramachandran plot is very good at determining dihedral angles, and there will be a Ramachandran plot on the exam so that you can look at your dihedral angles and determine what's your best alpha helical or beta secondary structure. Let's look now back to tertiary structure consideration. Again, we're just focusing on the R groups. Pay close attention to disulfide bonds. And all of these are going to be factors that play a role in side chains coming together. Okay, the hydrophobic effect, the charged polar effect, even some polar amino acids would like to interact with water. So their side chains will interact with water. That would drive a tertiary structure. Hydrogen bonding, and also just plain ionic interactions. And then finally, reaching a thermodynamic minimum. So combining points 1 through 6, you really get the lowest energy state. So here are examples of some fully folded proteins. This is an individual protein, so we're not talking about a protein-protein interaction. We're talking about a single globular chain. And you can appreciate and take a look at these pictures. You can see here the different types of folds. You can imagine going from the primary amino acid sequence to this. And what's amazing is that this has to fulfill a very vital function to the cell. So remember, for all types of structure, there is going to be function. There is a structure-function relationship. All right. So a couple of elements here, a couple of keys. We can connect beta strands with random coil. It could be along the plane or above the plane. So these are just ways we combine things to actually achieve that fully folded structure. Usually random connects secondary structure. And then on top of that, don't forget you have tertiary structure. Finally, quaternary structure. We'll talk more about that when we talk about hemoglobin. Hemoglobin is your classic example of quaternary structure. But I decided to show you another example of quaternary structure. This is copper zinc superoxide dismutase. This is the protein that's implicated in ALS, amyotrophic lateral sclerosis. There's a big push for this disease and finding a cure with the ice bucket challenge, which took place 2 or 3 years ago. And you can notice the wild type, or the correct native form of the protein, is a dimer. Also notice that you have copper and zinc. So a lot of proteins need help. In this particular case, copper and zinc are metals that facilitate and aid in the function of superoxide dismutase. The function of this protein, which is an enzyme, is to detoxify radicals, usually hydroxyl radicals or oxygen radicals, and detoxify them to water. It's a dismutation reaction where the oxidation state will change so that the radical can have a stable oxidation state and have a paired form of electrons. So it detoxifies radicals. It has a very, very important and vital function. And here I've shown you the PDB file, the protein data bank file, for the dimer form. Most of the subunit interactions are non-covalent. Non-covalent. So that means hydrophobic, ionic, polar, non-polar. These stabilize subunit interactions for a protein which will have a quaternary structure. It's these same non-covalent interactions that stabilize the hemoglobin tetramer. All right, we're kind of jumping ship between secondary and tertiary structure, but I think it's important to recognize what secondary structure is and what tertiary structure is, and some of the main important consequences of both of them. And here we have an important consequence of secondary structure, and that is this landmark paper published around 1978 by Chou and Fasman. Gerald Fasman and Peter Chou, T. Chou and G. Fasman. And they looked at 1978, they looked at the primary amino acid sequence of about 20 or so proteins whose structure is known. And when we talk about the structure, we're talking about every atom in three-dimensional space of that protein was solved, its X, Y, and Z coordinates. Usually they're solved by X-ray crystallography. And they looked at these 20 or so proteins whose early crystal structures have been determined, and they looked specifically at all 20 amino acid residues. From all 20 amino acid residues, they are able to actually designate a propensity P. That propensity P represents the ability of an amino acid to reside in either an alpha helical secondary structure or a beta strand secondary structure. And now you have the first primordial predictive manner known as the Chou-Fasman rules. They still exist today. Obviously, the technology has vastly improved. And you can see here, very landmark for its time, these Chou-Fasman rules. Now, if you read the paper, the rules are very specific. There's about 10 to 12 rules, and I don't know them off the top of my head. But it's about a 40-page paper. So, for example, one rule may be, if serine is beside an alanine and it's 2 amino acids away from an isoleucine, then you have a stretch where that serine is going to be in a beta sheet. And, like that, you have all these different rules and regulations. But the net effect is that they were able to map a propensity. There's also a lot of statistics in this paper. So this P stands for propensity, a statistical probability that you'll find an alanine in an alpha helix and an alanine in a beta strand. So if you look at the highest number here, it's about 1.45. Methionine is primarily found in alpha helices. And if you look at the lowest number here, just by eye, 0.57, you'd find proline in a very minimal and alpha helical structure based upon the 20 or so early protein structures that were determined. Same thing here for a beta strand. So you actually have the propensity of particular amino acids to reside in a particular secondary structure. Since then, people have actually modified and improved on this. We have more structures out there in the protein data bank. And you have the Kite-Doolittle plots. You have this predictions incorporated into membrane proteins. So these guys really started it. And like I said before, it's really a landmark paper in the field. Now we'll switch gears, and I'm only going to talk about 2 structural proteins. The other proteins that we will focus on in this class are going to be more globular proteins. But realize proteins can have a role in architecture as well. And 2 proteins that we're going to talk about that have a role in structural architecture are collagen and keratin. Now, what do I mean by architecture? I basically mean the ability to maintain cellular integrity, cellular skeletal nature, a rigidness, a hardness to the cell, which in turn implies a rigidness to the hardness to your extracellular matrix, to all the things that are important for maintaining the ability of a tissue or an organ to be still. So imagine if you're jumping up and down or walking. It tends to require a lot of support. So you can call these structural proteins or support proteins. So the first one we want to talk about is keratin. So keratin is a structural role in terms of providing functionality and rigidity to hair. So you see a lot of shampoo products, brag about revitalizing keratin. They're really talking about revitalizing this protein. It also imparts a lot of strength to collagen, which connects muscle to bone, muscle to tissue. And so all of these are very much habituated in the extracellular matrix. That's their location in the body. And if you look at the structure of keratin, you notice you have higher order structure. That's going to really discriminate a structural protein from a globular protein, which just collapses into its native 3-dimensional state. So you have something that's very fibrous and really organizes with other units of itself. So the general cartoon model of keratin is a helical coil, where the helical coils, also known as a coiled coil, forms a supra secondary structure with other coiled coils. So it becomes like a superstructure. And those coiled coils just form into this nice tube-like structure. So you start with the dimer, a coiled coil dimer. The coiled coil dimers interact with one another. And then all of these coiled coil dimers interact with other coiled coil dimers in a big tube. And now you have a fibrous formation. So really higher and higher order structure. And that gives you that nice rigidity and texture of extracellular matrix as well as hair. So again, architectural proteins and structural proteins. Not going to focus on that in this course, but they are out there. Okay, you may have heard of actin or microfilaments. These are also structural proteins. All right, notice the higher dimensionality. We start off with a coiled coil, an alpha helix. We have disulfide bonds to provide additional rigidity. And the coiled coils interact with one another to form a protofibril. The protofibril interact to form a microfibril. The microfibril aggregate together and associate to form a macrofibril. And the macrofibril, all of these macrofibrils come together to form the cortex. And within the cortex, you have the cuticle, and then from the cuticle, you have a scale. So you're basically building from a coiled coil all the way to a strand of hair. So really building, 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 and building. Again, structural proteins important in the alpha keratins. Another very important protein is collagen. This is the second type of structural protein. And here we have a triple helix. So collagen is generally associated with the triple helix. And it also is associated with some amino acids that you typically wouldn't find in amino acids. You have your hydroxyproline, hydroxylysine, and these form hydrogen bonds that could really stabilize the triple helical nature of collagen. So collagen has different types and different functionalities. I usually associate collagen with the extracellular matrix and that ability to, imagine you're running or jumping or squatting, or you have to do some vigorous physical exercise. Well, to keep all of those bones and joints and your extracellular matrix in place, you need collagen. Okay? Collagen also can absorb water and release water. It has that spongy nature to it. And when people, usually through old age, have a disintegration of collagen, that's when, people have difficulty in their gait, people have difficulty with their mobility. We're really talking about type 9 and type 12 collagen. We also have type 4 and type 7 collagen that's involved in basement cell membranes and intestinal cellular membranes. And then you have the collagen that is known for its elasticity, collagen 1, collagen 2, collagen 3. So a lot of mutations in collagen cause a tremendous amount of disease. There's no other protein that is associated with so many diseases than collagen, simply because of the fact that mutations can occur in type 1, 2, 3, 4, 7, 9, or 12. And here, type 1, 2, and 3 collagens give that elasticity to skin, flexibility, tendons, and vessels. These are really extracellular matrix components. Elasticity with blood vessels. So different collagens, different types of modifications, but all collagens are unified by that triple helix. And here we have one unique thing about collagen is its uniqueness in terms of its amino acid residues. You see here you have hydroxyl groups, hydroxyproline and hydroxylysine. These are added post-translationally. So these are post-translational modifications that is done after the ribosome synthesizes the protein. So it's done after translation. And this hydroxylation is actually vitamin C dependent. So that vitamin C dependence makes vitamin C essential for health. Our body does not produce vitamin C. We need to get it from our body. And so deficiency in vitamin C actually causes scurvy. So without vitamin C or deficiency in vitamin C, you lose the ability of that reaction to hydroxylate these residues, and automatically you lose the integrity of collagen. Henceforth, you lose that triple helix vibrancy. And these people, you notice how collagen is involved in all these different forms and blood vessels and membranes and ligaments and maintenance. And without vitamin C and that vitamin C dependent hydroxylation reaction, you lose collagen's ability to perform its function, and that disease is known as scurvy. Scurvy is the deficiency of vitamin C, which prevents collagen from functioning because you lose the hydroxylation reaction. Another thing about collagen is its conserved tripeptide repeat, glycine, proline, hydroxyproline. Notice that glycine is found in alpha helix. For whatever reason, glycine likes to associate with alpha helices. Proline and then hydroxyproline. You can actually get this tripeptide repeat within the alpha helix up to 333 times. And also don't forget you have that hydroxylysine, and then you have that hydroxyproline as well. Like I stated before, hydroxylation of proline and lysine, these post-translational modifications, is vitamin C dependent, and that disease resulting from the lack of intake of vitamin C is scurvy. A lot of diseases associated with mutations in collagen. One of them is Ehlers-Danlos syndrome. This is the stretchy skin syndrome. That is linked to some mutations in collagen. This is a scurvy, the legs of a patient who has not taken enough vitamin C. So you can see his skin is very easily bruisable, and it has a black and bluish tinge to it. The collagen is really not working properly. Also, his legs are bow-legged, so it's not a normal gait. It's a bow-legged, so the actual knees protrude. This one protrudes that way, that one protrudes the other way. It's not really straight as you would normally expect with someone who has normal collagen. So a number of diseases. There's also brittle bone syndrome, so that's important to realize that's an effect of a collagen mutation. Brittle bone syndrome is also known as osteogenesis imperfecta, where the bone structure is not tenable. Remember, collagen is part of the extracellular matrix, so we would expect for it to interact with bone helix and a second helix. They're all coiled together. Here, one triple helix is interacting with the bottom triple helix. I can make this appear a little bit better if I hide the main chains and the side chains, and you can see here the association of the triple helix. You can imagine this ordering above and below, and three-dimensionally to give you that rigidity that collagen is known for. See the crystal structure of keratin. So keratin along with collagen are really hard to make. There's a big move to actually synthesize these, but for now you only get synthetic peptides or synthetic segments of collagen or keratin. And so again, the real version of collagen or keratin that's found in the body would be multiple complexes into a very highly ordered three-dimensional structure. So let us, and then form your macrofibrils ultimately till you get to the cortex of the hair molecule or the hair strand. Also, you find keratin in a lot of extracellular matrix components.